In this video, we're going to cover inverse trig functions, specifically sine inverse. So, to do this, we're going to start off by identifying what function we're referring to. Again, sine of x being the graph that initially starts here, and again looks something like this in the basic form, such that this is 2 pi. While looking at this particular type of function, this continues backwards, again, this being a value of pi negatively, this being a value of pi positively, and again, keep in mind that this thing continues on forever. So we'll hit a 3 pi location somewhere about here. So the issue with this particular type of function is that if we're going to identify its inverse, we have to make sure that we understand that the reflection over this dotted line, this y equals x line, that it creates a function. So very much like that of the quadratic, where you have a function that looks like this, and you reflect it over that dotted line, it looks like this. This is no longer a function. So when we go to identify its inverse, we either refer to this section with a specific domain, or this section with a specific domain. So what we're going to do is we're going to do the same thing with the sine function when we go to define its inverse. Now, if I called this y equals the sine of x, the way that we would identify the inverse is we'd swap x and y, and then we'd solve for the new y. Well, solving for the new y in that step would provide us with y is equal to sine inverse. Now keep in mind there's no nice way to notate a trig function of its inverse. The only other way that you could identify an inverse trig function is arc sine. You might see this notation in other courses and or other textbooks, but these two notations mean the same thing. Sine inverse of x or arc sine of x. Arc sine is the same thing as inverse of sine. Now, let's make sure that we understand this notation. F inverse of x is then equal to sine inverse of x. And again, notice how I don't use the word power. Nowhere in there did I say power. I was referring to sine inverse as being the function inverse. And again, that superscript of a -1 refers to that inverse. So the way that we're going to go ahead and identify this inverse function is by looking at this whole function flipped. So what would that look like? I'm going to draw that in a small scale here, such that this is the new x and this is the new y. These are all going to be positive values of x and y, so they should be positive values of x and y, and they should go like this and continue on forever like that, as well as in this direction here. So I want to go ahead and pick a section of values such that this will end up passing the vertical line test. Again, for it to pass the vertical line test, it can't have multiple locations where that vertical line passes through. I also want to make sure that the values that I select for this is going to be a continuous section of values. So if I were to just say, let's try from 0 to pi, you'll notice how if I try 0 to pi, if I try the vertical line test, it's going to fail because it's going to pass here, and then it's going to pass here. So this section of information isn't enough. Now also you'll notice then that going from 0 to 2 pi isn't quite enough, which is where we generally cycle a single cycle of the sine function. So 0 to 2 pi isn't going to work because, again, it's going to fail here, it's going to fail here. Also notice that if I don't go further from 0 to pi, it doesn't cover half of the values in the sine function. So what we're going to do is we're going to select a very specific set of values, and when we cut that set of values, this is the generic, this is the common way that we refer to the sine inverse function. So I'm going to cut it right here, and I'm going to cut it right here. Now if we recall that location, that high point on the sine function, that's supposed to be a pi over 2 location. And this one down here then would be a negative pi over 2 location. So when I select the sine inverse function, it is domain-wise defined from negative pi over 2 to pi over 2, specifically in such a way that we are including those two locations. So that sine function, if we were to graph it on an xy coordinate plane, would actually look something like this, where I have this location is pi over 2, this location down here about halfway through is pi over 2 negative. I'm going to have a value of somewhere in here is going to be a positive 1, and somewhere over here is going to be a negative 1. We're going to go from here up to that point right there, and then from there we're going to do the same thing, but we're going to go to that point right there. And that right there is your sine inverse function. Now, we define the sine inverse function to only evaluate this set of values. Okay, so this is the values that we're allowed to plug into this sine inverse function that will give us back the y values of this graph. It's also important for us to know what we're actually referring to in terms of f of x equals sine of x and f inverse of x equals to sine inverse of x. For the sine inverse, or for the sine function, remember, I plug an angle into here, and I get back a ratio of two sides of a triangle. Again, I'm going to get a number of some form. Again, I plug an angle in, I get back a number. In this situation, I'm going to go ahead and, I'm sorry, this isn't correct. This is supposed to be a set of y values. We're going to plug in a ratio value into here, meaning we're going to plug a number into the sine inverse function, and it's going to spit back an angle measure. So that's the value that's the setup of concepts that we're going to be working with. What we're really doing in the way that I have it appropriately written is up here, we are cutting the sine original function in this way in terms of its domain to create an inverse function. When we cut this domain set of values, it will then become its range set of values down here, creating that inverse function. You'll also know that if I want to go ahead and identify the x values that I'm going to get back, well, they're going to be somewhere between -1 and 1. That is relatively straightforward and I hope easy to see. Again, here's the x value of 1, here's the x value of -1 and 1, and I include all values from one to the other. You'll also notice, again, same concept is from -pi/2 to pi/2 in terms of the y values, again, the angle values that I can get back. So again, one more time, I plug an angle into sine, I get back a numerical value. That numerical value, one more time, represents a ratio of two sides of a triangle. In the sine inverse function, I, however, will plug in a ratio of two sides, a number between -1 and 1, and I will get back one of these sets of angle values between -pi/2 and pi/2. So there's an infinite number of actual y values that we could pick. We're reducing it specifically to this set of values. So that's how we're going to define the sine inverse function. And anytime that I'm working with the sine inverse function now, I'm simply going to go ahead and work with that set of values. So the first example we're going to look at for sine inverse is the sine inverse of, say, radical 2/2. Now, the most appropriate way to evaluate inverse trig functions is to look back to the unit circle. We already know all the values from the unit circle. We've worked with them before. So in this case, for sine inverse values, I'm working between a -pi/2 and a pi/2 of angle measures, meaning that all the angle values that I'm allowed to pick sit in the first and the fourth quadrant. It's all in this set of values right here. That section of information is where sine inverse is going to be defined. So, because it's important for us to note, the middle section value is going to have a radical 2/2, comma radical 2/2. The sine value, remember, is the y value in the unit circle. And again, this could get very confusing with us using y's and x's and all this other information. Well, this is, again, just a notational concept. The x value generally represents the cosine, the y value represents the sine value. So in this case, my angle measure should correlate with this middle dash. I know that the angle measure at that location is either 45 degrees or, more appropriately, pi/4. Now, the reason why, again, we narrow it down to this section of values is because technically there's another location over here where the sine value would spit back radical 2/2. Again, we'd have negative radical 2/2, comma radical 2/2, but this location is 1, 2, 3 pi/4. But remember, we're removing the duplicity of this. So we're simply going to narrow it down to a single set of values that we can get back. Pi/4 is in the range of values that we can get back. That's the set of values. That's the value we're looking for. Again, technically there's two locations, but there's only one location in this situation. Now this would change. This rule would be slightly different if we were looking at, say, sine of y equals to radical 2/2. If I had something that looked like this, then it would be different. There are multiple possible answers for y. If I take the inverse function, it'll narrow my scope and very specifically look for this one point. So given a situation like this, we're looking for potentially, depending on what the question says, find all angle measures that provide this situation or this equation to be true. Well, then we would solve for that y value such that we can find every single point. But I digress in terms of the concept of what we're working with. In most cases, for this section right now, we're just playing with this concept right here. So another example we might look at is, say, the sine inverse of a negative radical 3/2. Again, the example is I want you to find the angle measure. The concept is sine of theta equals to a negative radical 3 over 2. For what angle does that work? And since we're really talking about an inverse trig function, we still only can work in the first and the fourth quadrant. Now I know that sine being a negative value has to be in this this fourth quadrant down here. And if we've forgotten the values, again, it starts at 1, 0. I'll fill in this one right here, radical 3 over 2, 1/2. So I know that this location up here is the one where the y value is the radical 3 over 2, which means that I'm looking at this location right here. So this value technically would be my 1/2, negative radical 3 over 2. And more appropriately, I'd have to figure out what angle measure that's going to be. Well, remember, if this value up here is technically pi over 6, pi over 4, pi over 3, then this value down here, yeah, you could count all the way around, but remember, we have to have it a value between negative pi over 2 and pi over 2. It has to be a continuous set of values for us the way that we've defined it. So in that case, I'm looking at a negative pi over 3. That's the set of values that would give me this thing to actually be what it is. So this thing is equal to a negative pi over 3. That's the angle measure that I'm looking for in respect to the sine function and how we have defined it in this particular case. Again, this is the general way that we refer to the sine inverse function. This is the domain and the range of the sine inverse function that is generally accepted.